this video, we are going to look at using both the root test and the ratio test to determine whether or not a series converges. And we're going to start with the ratio test. So to start off with the ratio test, you first have to be working with a series that has non-zero terms. So you have to make sure that none of the terms in your series could possibly be zero. If that is the case, then in order to use the ratio test, you have to look at the limit of a ratio. In particular, you look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And if that limit comes out to be smaller than 1, then that tells you that your series converges absolutely. But if you evaluate that limit, and that limit comes out to be either greater than 1, or if that limit comes out to be positive or negative infinity, in either one of those two cases, then your series would diverge. So we talked about what happens if your limit is less than 1. We've talked about what happens if your limit is 1. And we've talked about what happens if your limit is less than 1, then it converges. If your limit is greater than 1, it diverges. If your limit is positive or negative infinity, the series diverges as well. But if this limit comes out to be equal to 1, then the ratio test does not tell us anything. And it's inconclusive, and we would need to go use another test in order to determine the convergence or divergence of our series. So let's look at an example. In example 1, we have a series, and the nth term of this series, just what's on the inside of it, is 2 to the n over n factorial. The first thing I will point out is that this is non-negative, right? This is nothing that's ever going to be equal to 0, because fractions can only equal 0 when their numerator is equal to 0. So because it's non-negative, we can look at the ratio test. The ratio test tells us we're going to need the nth plus 1 term of the series. So I'm going to just replace n with n plus 1. So I have 2 to the n plus 1 now over n plus 1 factorial. And now I'm going to look at the limit involved in the ratio test. So I'm going to start plugging in the different terms. So we have the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial. That is our a sub n plus 1. I went ahead and put that in the numerator from there. And then that will be divided by a sub n, which is 2 to the n over n factorial. Mind you, all of this is still on the inside of the absolute value, which is what we're going to talk about next, because both of those expressions, not only are they non-zero, but they're never negative, because 2 to any power is never going to be negative, and those factorials in the denominator are also never going to be negative. So because they're never negative, I can drop the absolute value bars. I don't have to write it anymore. I'm also going to go ahead and multiply by the reciprocal since we are dividing fractions. And it looks like I've dropped a factorial here. Yeah. So this is the one I'm going to flip. So we're doing keep, change, flip to divide fractions, divide by the reciprocal. So now we're left with this expression here, and at this point it's going to start to become more clear why we would even want to use the ratio test on a series like this. Because remember, when we take the test or the quiz or the final, I'm not going to explicitly say use the ratio test to determine convergence. So when we start to simplify this expression, there are things that can cancel, and to see that, I'm going to rewrite the 2 to the n plus 1. I'm going to break it apart as a 2 to the n times a 2 to the 1. So we know rules of exponents tells us that to combine the n and that 1, to combine these exponents, we would have added them, which is how we would have gotten back to that. So I'm just breaking it apart. In the denominator, the n plus 1 factorial, I'm going to start expanding that. So we know that n plus 1 factorial is n plus 1 times n minus 1, so on and so forth. But I'm not going to list those out. I'm just going to put it as n plus 1 times n plus 1 factorial. And then I'll go ahead and write the second fraction that we had. So hopefully now you can see a bunch of things will be able to cancel, or at least 2 things will be able to cancel. The factorials will cancel, and in addition, the 2 to the n will cancel, and that will just leave us with the limit as n approaches infinity of 2 over n plus 1. We can evaluate that limit. The degree of the denominator is greater than the degree of the numerator, so this limit goes to 0. What does that tell us from the ratio test? Well, it tells us that this series converges absolutely. And I know that it converges absolutely because the limit that we evaluated came out to be something that was less than 1. So one indication when you're working with a series that you might want to do the ratio test is if you see factorials. So factorials, I'm just going to put try ratio test, because when we work with a ratio, we're able to cancel out some of those factorials that we'll see in that expression. Let's look at example 2. I'm going to get started the same way and just identify a sub n, which is just everything we see on the inside of the series. And I'm also going to go ahead and identify a sub n plus 1, which just means we're going to be replacing n with n plus 1. So instead of n squared, we have n plus 1 squared. Instead of 2 to the n plus 1, we have 2 to the n plus 1, which would be n plus 2. And then in the denominator down here, I have 3 to the n plus 1. Yet again, both of our terms are non-negative. It's not possible that either of these terms will ever be negative. One thing that may be a point of concern is that we do have a 0 term. So when n is equal to 0, this first term right here, a sub n, would be equal to 0. But that's the only time that it would ever be equal to 0, because those numerators with that exponential and that quadratic are never again going to be equal to 0. So with just one 0 term, that is okay, and we can proceed with the ratio test. So I'm going to go ahead and start looking at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. We've already talked about how we do not need to write the absolute value because nothing here is ever going to be negative. I'm going to start with the a sub n plus 1. And we're going to take this and divide it by a sub n. So since we are dividing by a sub n, I'm going to multiply by the reciprocal of a sub n. So I'm going to go ahead and flip a sub n. I'm going to go ahead and start rewriting this so that we can see some things that are going to cancel. I'll leave this n plus 2 squared. We don't have to expand that out in order to evaluate the limit. The 2 to the n plus 2, I'm going to break up as a 2 to the n plus 1 times a 2 to the 1. Okay, so I broke that up. And the reason, before we go any further, I'll talk why I broke it up like that. So I just went ahead and wrote the second fraction that was down there. I broke it up like that because of this 2 to the n plus 1 right here that it can cancel with. I'll go ahead and finish filling out the denominator from the first term. It's 3 to the n plus 1, but I'm going to break it up into a 3 to the n times a 3 to the 1 so that I can cancel this 3 to the n with that 3 to the n. So we see that things cancel. Let's look at what we are left with. We are left with the limit as n approaches infinity of, let's see, what we still have is we still have this n plus 2 squared, and we still have that 2 in the top. So we have a 2n plus 2 squared in the numerator, and then in the denominator we still have this 3, and we still have that n squared. So we have a 3n squared in the denominator. We want to evaluate this limit. One of the first things we learned back in Calc 1 was taking limits of ratio expressions. What's important here is that the degree of the numerator is equal to the degree of the denominator. And when these degrees are equal, we look at the ratio of the leading coefficients. So this limit comes out to be 2/3, which is less than 1. Because that limit is less than 1, we are able to conclude that this series converges absolutely by the ratio test. Please do not confuse. We are not saying that this series converges to 2/3. We are not saying that if we add up everything in this series, we will get 2/3. No. The ratio test does not tell us what the series converges to. it tells us if the series converges or not. And we're only able to tell that if that limit was not equal to 1. Let's look at example 3. I'm going to go ahead and set up a sub n plus 1. Very similarly, we will see that our terms are non-zero and non-negative, so we will not need the absolute value when we start evaluating our limit. So there's a sub n and a sub n plus 1. Both of these are always greater than 0, so I'm going to go ahead and start looking at the limit as n approaches infinity of a sub n plus 1, which is going to be divided by a sub n, so I'm going to multiply by the reciprocal of a sub n. I'm going to go ahead and do a little bit of algebra to start simplifying this expression. So I'm going to rewrite this n plus 1 to the n plus 1 as an n plus 1 to the n, and then just another n plus 1 that's to the 1. In the denominator, instead of the n plus 1 factorial, I'm going to expand this out a little bit as an n plus 1 times an n factorial. So same techniques that we've seen before so that some things can cancel. So what cancels here is this n factorial cancels with that n factorial, and then this n plus 1 cancels with this n plus 1 in the denominator. And what we're left with is the limit as n approaches infinity of n plus 1 to the n divided by n to the n. Notice that both the numerator and the denominator have an exponent of n. So I could combine this into simply one fraction of n plus 1 over n, which is all raised to the n power, because we would apply the exponent to everything in the numerator, and we would apply the exponent to everything in the denominator, which is the exact same thing that we had. Within those parentheses, we can simplify n plus 1 over n, because we can think of this as n over n, which is 1, plus 1 over n, which can't simplify, still all raised to the n. And this is a limit that we have seen several times before. At this point, we're used to seeing it usually with x instead of n. The first time we looked at this limit, if you look back to where we learned about L'Hopital's rule and indeterminate forms, back in chapter 5, you will see where we evaluated this limit and calculated that it was the natural number e, which is about 2.78, which is greater than 1. So because we're getting a limit that is greater than 1, this series diverges by the ratio test. So I'm going to start example 4, but we are not going to finish it because we're going to realize that the ratio test is inconclusive, and then I'm going to ask you all to go back and use another test that we have already learned. So first things first, let's get started and identify a sub n, which is just everything that's on the inside of our summation. And then let's identify a sub n plus 1. So I'm just going to go and replace n with n plus 1 with everything that's on the inside of our sum. Both of these expressions we cannot say are non-negative because we have that negative 1 to the n there. I do know that none of them will equal 0, but I don't know that none of them will ever be negative. So I will need to keep the absolute value bars as we go on to evaluate our limit. So I'm going to go ahead and start plugging into the inside of these absolute value bars. First I'm going to put a sub n plus 1. That's what goes in the numerator, and it does matter what order you put these in because the order in which we divide does matter. We are dividing by a sub n, so I'm going to multiply by the reciprocal of a sub n. And let's work on simplifying this expression that we have now on the inside of this absolute value. So with the negative 1 to the n plus 1 and the negative 1 to the n, those two pieces are either going to equal 1 or they're going to equal negative 1. And they're on the inside of an absolute value. So even if they're negative 1, they will become a positive 1. So those pieces are not going to change the absolute value on the inside because they're either positive 1 or they're negative 1. So now I can drop the absolute value and realize I'm just left with the square root of n plus 1 multiplied by an n plus 1 divided by an n plus 2 multiplied by the square root of n. And if I were to take this limit, we need to think about the degree of the numerator and the degree of the denominator. So here we have a square root and an n to the first. So in the numerator, it's as if the degree was 3/2 when I add the 1/2 to the 1. And we have a similar thing going on in the bottom because we have this 1 being added to that 1/2. So these degrees are equal, which would mean that we would take the ratio of the leading coefficients. The leading coefficients are 1. So that tells us that the ratio test is inconclusive. With the ratio test being inconclusive, we're going to have to try something else in order to determine the convergence or divergence for this series. So at this point, I would ask that you all go back and look at example 4, which is an alternating series. So that leaves everything else on the inside of your series to be your a sub n. If you were looking at this in terms of an alternating series, your a sub n would have been everything except for that negative 1 to the n. If you can show that the limit as n goes to infinity of that goes to 0, and if you can show that a sub n is decreasing, so you would want to show that the nth plus 1 term is less than the nth term, then you could conclude something using the alternating series test. The second test we're going to look at is the root test. It's very similar to the ratio test, similar in the sense that we look at a limit. So we look at the limit as n approaches infinity of the nth root of the absolute value of a sub n. And depending on the value of this limit, we may or may not be able to determine whether the series converges or diverges. So first, I'm just writing this limit repeatedly. This is the nth root of the absolute value of a sub n. And we're going to then take a look and see, well, what happens depending on the value that we get for this limit. So if we evaluate this limit and it comes out to be less than 1, then our series converges absolutely. Our series will diverge if the limit came out to be greater than 1, or if the limit comes out to be positive or negative infinity. And the test is inconclusive if the limit is equal to 1. So hopefully you see how that's similar to the ratio test. So when would we want to use the root test to work on determining convergence for a series? If what's on the inside of our sum has n in the exponent, that's a good indication that you may want to try using the root test. And the reason that I say that is because let's look at what happens once I take the limit as n goes to infinity of the nth root of the absolute value of a sub n. Remember, a sub n is just what's on the inside of the summation. So when I actually plug that in, we have the limit as n approaches infinity of the nth root of the absolute value of e to the 2n over n to the n. There's a couple of things here. E to the 2n over n to the n is positive, so I don't really need to write the absolute value anymore. So we could do that simply because this is greater than 0. And secondly, this whole nth root right here could be rewritten. Instead of writing it as a radical, we could rewrite it as a rational power by just taking everything that was under that radical and now writing it to the 1/nth power. Right? That's the same thing. The nth root and the 1/nth power are the same thing. So now I can use properties of exponents and actually distribute that exponent of 1 over n into both the numerator and the denominator, which leaves us with the limit as n approaches infinity of e squared over n. Because I'm taking the 2n, multiplying it by 1 over n, those n's cancel, leaving me with the 2 on the e. And then down here, I'm taking the n and multiplying it by 1 over n, which just leaves me with a 1, which is why you don't see an exponent down there on that n. Now this limit, as n goes to infinity, is going to go to 0. The numerator is simply a number. It is e squared. The denominator is n. It's getting very, very big. 0 is less than 1, which tells us that this series converges absolutely by the root test. So again, biggest takeaway, I think, from these two different tests is, I think, when you would want to use them. You would want to use something like the root test if on the inside of your summation you're seeing n's in the exponent. Because if you're seeing n's in the exponent, the root test is going to come in and tell you to do a 1 over n power, and that's going to help cancel some of those things out. For the ratio test, you may find it helpful to use the ratio test if you're seeing factorials in your summation, because some of your factorials will cancel out as you start to look at that ratio in the limit of the ratio test. Secondly, you may also find it helpful to use the ratio test if you're seeing n's in your exponent, but you see additional terms up there as well. Because here I do see an n in the exponent, and you may say, oh, well, why not do the root test? Well, because it also has this plus 1. But if I do the ratio test, I might be able to cancel out that plus 1, which is what we were able to do later on in that problem.